So let me actually try to be close to the previous lecture. You should think of my lectures and Mauro's as addressing the same question, except he starts high on his knowledge of homotopy theory and spaces and walks down towards us. And I start at the other end as a classical algebraic geometer who at some point realized that classical methods are not enough. And so I'm climbing up towards Mauro, and maybe we will meet at some point. So in particular, we had, I mentioned, and so did Mauro, the cotangent complex. And I would like to give an idea of the classical meaning of this term. So the point is, let me start again with R, a finitely generated C algebra. And in some sense, the idea is I would like this to be smooth, but in general, it is not. And so what I can do is there is something like a simplicial resolution, which would work also over any field or with no field. And this is what Illusi does. But I cannot present this to you because I cannot fit it in the time required, and also I don't know it, so I would have to just copy the book of Illusi to you, which seems useless. And instead, I will describe a differential graded resolution. And this is based, of course, on stuff that Mauro defined. So he defined, remember, what is a commutative differential graded algebra. He insisted also in connective, which I would use a slightly, then connective is what I would usually call in degrees at most 0. But this is just, as he was saying, this is a combination of the notion of complex of C vector spaces plus graded commutative algebra, where, of course, graded commutative means, so graded means each of these have in common the notion of graded vector space. So if a graded vector space is a direct sum a priori with integer coefficients, then to get a complex, you have to add a differential such that d composed d is 0. And to get a graded commutative algebra, you have to give an associative product with the property that it respects grading in the obvious sense, and it's graded commutative in the sense that things and then you want a compatibility which is graded Leibniz. And so d of AB is dA times B plus minus 1 to the degree of A times dB. And this is, of course, something we are all familiar with. For instance, a typical example is that if M is a manifold, I mean a real C infinity manifold, then I can just take A P to be A PM to be complex valued differential P forms. and with product, the wedge product, and differential, the differential of P forms. And what we can do is notice that in this case we know that this is a complex, that the cohomology of this algebra is a graded commutative algebra, and it's the ramp cohomology of M with complex coefficients. So this is really, notice however that this is not connective, because in fact it's always in positive degree, not in negative degrees. So we are going in the wrong, so to speak, in the wrong direction, but at least it helps me remember how the definitions are. And so what we want instead, so again let me discuss what is a quasi-free CDGA. It's one which is graded free as commutative graded algebra. So it means that if I forget the differential, it's just I put free variables in a bunch of degrees. So of course, if I put the variables in degree 0, I get usual polynomials, but in general. And let me give you an example, which is an example that Mauro had. So let's assume that you have X inside AN, okay? And it's given by the ideal of X. You have R explicit generators. So this is will depend on my choice of generators. And then what I can do is I can do a quasi-free algebra. First of all, I define it as K of x1, xn in degree 0, and y1, yr in degree -1. And so this is well defined. It's a free commutative graded algebra. So it means the x commute and the y anti-commute. Notice that this, if you want, this is just a wedge algebra of an r-dimensional free module. And now, of course, I can define the differential by requiring this. And what I get is I get the Koszul algebra associated. And as Mauro was saying, if F1, Fr is a regular sequence, this and maybe I will also add for security that X is reduced. It's just, I'll just throw this in for my happiness. It's probably not necessary, but this is what I'm familiar with. Then what you get is that the algebra so defined has the property that H0 of A, well, this is kind of clear by the way I've defined it, is indeed K of x1, xn mod I, and so it's just the algebra of sections of X. But also, there is no other cohomology. And so what I get in this case is that I have a homomorphism of graded algebras. I had called this R. Let me call R this one. And this is a homomorphism of CDGAs. and it's a quasi-isomorphism, which I often write like this. So in this case, what we have done is we have taken our R and found an A dot which is quasi-free and is equivalent in the derived sense, as a complex. And now what we can do, of course, is show there is a fact. It's not particularly difficult, but it will take extra time, is that for any R finitely generated C algebra, you can find such a resolution. So this is non-derived, this is classical, this is all in degree 0, and this is all in degree 0, which is a quasi-isomorphism with A dot. Quasi-free. And of course, it's not unique, and you can, in fact, you don't even need finitely generated. You can always do it. And the finite generation is for my personal happiness and for what I want to do later. And of course, it's clearly not unique. But what you can do is show that a construction, you can get a universal one, at least in the simplicial level. And what you can do with it, you can associate to this A dot, it's a cotangent. Well, how shall I put it? Should I call it a cotangent module or its cotangent complex? Because after all, this is A dot as an algebra, is a free algebra. I told you it's quasi-free. So as a module, this is a, let me put it, call it just omega, and this is just a graded A dot module generated by the differential of the free generators as a quasi-free algebra. So this means that as a graded module, it's just free with generators in different degrees. And then it also has a complex structure, so it has a differential, which I now write with a strange delta because my D is already occupied. And the idea is that if you have to define the differential, of course I want it to be compatible with a 1 on A, so I will not discuss how, I just have to define it on the generators. And on the generators, it is the differential, the differential of, yeah, this is, okay, sorry, I should call this delta. And then I have a differential of delta U is delta of du. And so I get this complex, which is free in a sense, but with differentials. And of course, it depends on A dot. But then what I can do is I can pull it back. And I can take LR to be this tensored with R. And then this is again a complex of free R modules in degrees smaller than 0. And what you get is that this object, so it gives you an element. Let me actually call it this. This is the cotangent complex, and it is an element of R mods, and in fact, it's all finitely generated, so there is nothing there. And the point is, does not depend on the choice of resolution. And this you can do for algebras, and in fact, as you can do it in such a canonical way that you can do it. So extensions of the same idea. So first of all, instead of working here, I have started working with differentials over k. But of course, I can do the same in a relative version. So I have Rs over R, and then I'm only interested in S differentials, and so I can find a resolution, quasi-free resolution over S. So you start putting S in degree 0, and then add the free variables in non-positive degrees. You do exactly the same argument, and what you get is a relative cotangent complex. And once you can do it for algebras, you can do it for schemes. So the same for these glues naturally, else you can be defined universally enough that for any morphism of schemes, you get a well-defined cotangent complex. And so that's, so what does, and as I said, this is the one we were mentioning, that it has these good properties, it completes the, and these are the good news. And the bad news is that this is not very well behaved. So you have that LF is 0 if and only if F is et al. LF is perfect in 0, 0, or as you may call it, just has one cohomology, the zeroth cohomology, which is locally free. And this is if and only if F is smooth. And finally, L is perfect in -1, 0, if and only if F is locally LCI. And this is a notion you are familiar with if you have studied intersection theory. This corresponds to the fact that locally we can factor it as X in M in Y. This is a regular embedding, and this is a smooth morphism. And in fact, I should maybe say that LF is, well, I will not write this, but this is basically the idea. In particular, for a regular embedding, LF is perfect in -1, -1. It's just the conormal sheaf. So this doesn't look like bad news. Actually, let me call this good news. But the bad news is that this is as far as our luck goes. So if F is not LCI, then in general, LF, then not in general, but always, is not bounded. So it can go off, it goes off to -infinity. So we were talking about higher tangent spaces. How new are higher tangent spaces, or how are higher tangent sheaves? And so how do you define it if X is a scheme and you take a point? How do you define the famous higher tangent spaces or higher tangent sheaves? Let me start with the spaces, which are easier. Well, then what you have is, of course, P embeds in X. And so you can take the cotangent complex and restrict it to P. Or if you want, you call this the inclusion. And you call this is the derived left pullback of Lx. And now this is a complex of P, but this P is spec C. And if you are working with spec C, of course, the derived category is not very exciting. It's just a direct sum of its cohomology groups. And so what you get is you define the ith tangent space to P in X to be the ith cohomology group of Lx restricted to P dual. So the idea is that, for instance, what you get is that T0 Px is just a usual tangent space. Notice the shift in grading from the deformation theory. So this time the tangent is actually in degree 0. It's because we are working with a scheme. And if we were working with an algebraic stack, there would be, and this whole thing would have a piece up to degree 1. So when I dualize, it would start with -1, and there would be a -1, which is the tangent to the automorphism group. So depending which literature you have, the indexing of the tangent spaces shifts by 1. Sorry about that. I wasn't born. Can't complain that it was personally me. But this is something you should get used to. And there is another one which is useful, which is this one. And this is the famous minimal obstruction space. So I told you that in general, under suitable conditions, many deformation functors have this. And this is the minimal obstruction space. So the idea is, remember, this here is generated, this is a vector space, so it's a spec sim of a vector space. So this is spec sim of CDX1 plus CDXN modulo the ideal generated by the DFJ. notice that what do I mean by this? I mean that this is a local construction, and so I can assume again that X is back C of x1, xn modulo f1, fr. And the other one is basically generated by the f1, fr. Says dimension r. Generated, well, this is generated by the dy1, dyr, but of course it's not everything, let me not just say, but it's related to these equations in a suitable sense. So the idea is, however, you can see that already in this case, we have a number of others are also defined. But what the bad news tells us is that if, so long as we don't move from LCI, in fact, what you get is something perfect, and otherwise you get all these things which are strange. But on the other hand, remember that when we look at moduli problems, and for instance, to again tie back to what Mauro was saying today, you look at the moduli of vector bundles over X projective. I don't think I need smooth here. Then what I have now is that for any, if I take M, this moduli stack, this is an algebraic Artin stack. And if I take what is a point in here, this is just a vector bundle. X, then I have that, remember I have the Ti in def E, Ti to the deformation factor of E was Hi of and E. And so taking into account this shift, it means that the ith tangent space at the point E of M is I plus 1 of the endomorphism of E. And in fact, it's you can see that if you take, since you are taking the moduli stack, you have the universal sheaf, universal bundle on X times M. You can consider the projection this way. And what you get is that these are the fibers of a perfect complex. So you can do R pi push forward of end E, and this is a complex on M, or if you want, you can take its dual, and this actually turns out to be something that behaves like a cotangent complex for us. Okay, so it has the property that it induces, so this behaves like a perfect cotangent complex in the sense that it induces these higher tangent spaces at every point. And so, if you ask me how, as a classical algebraic geometer, you feel the need for derived geometry, is here what we do is we go to people who understand this stuff and say, okay, can I do, so this looks to me, so this is evidence of the following fact, that there exists a derived version of this moduli space such that, so what do I mean by derived version? Remember what Mauro just said? He said that as far as the points go, as far as the topology goes, the derived space is the same as the non-derived one. In fact, what we have is, in some sense, that the classical moduli has what I would like to call a closed embedding, but if I don't want to call it a closed embedding, I certainly have a map to the derived space, which corresponds to the fact that if you have locally your algebra that maps to its pi 0. And so you have classical maps to derived, and what I expect is that this one here has this some version of this complex, and then when I pull it back, so that the cotangent complex of M derived restricted to M is actually this. E dual. So the idea is, why do I want this derived structure to be there? Again, because it would justify at every level the fact that these natural things exist, and in some sense they are actually much more computable. So similarly for moduli of, say, smooth projective varieties, this is of course a very technical question, because notice that this is in general not an algebraic stack, but you can get it algebraic, for instance, if KV is ample, or minus KV is ample, all you work with polarized varieties. So you fix an ample line bundle, and then you get an algebraic stack. And let's not look at this case. It's not incredibly different, but it's notationally more complicated. And we are in the same situation, that the tangent space at one point to this moduli is hi plus 1 of the TV. And so again, here we would want a derived, we expect a derived structure. And notice the richness of the derived structure is that we get a lot more perfect cotangent complexes. And the perfect cotangent complex is very good, because, for instance, you can define, what is the advantage of the perfect cotangent complex is that you can define dimension, you can define its determinant, you can, if it's in -1, 0, you can use it to define virtual classes in a number of contexts. There's a virtual class virtual structure sheaf. So this is a very good thing. And what we have is that derived geometry shows us a deformation theory, very classical deformation theory, points us in that direction. And I would like to mention something, again, review what Mauro did in a more classical version. As we were saying, let's go back to this example of working with P1 and viewing it as a U0 union U1 glued along this intersection. Or more generally, we can work with X as smooth projective variety, and then we always have a similar finite decomposition in affines. And the point is that if U is affine, in some sense, from a derived viewpoint, vect n of U, the moduli of rank n bundles, is, so to speak, trivial infinitesimally. Is infinitesimally trivial. Because the tangents are all cohomology, and if U is affine, they become 0. So what this tells you is why we do not work with this. This is not algebraic, because of course we know that this is non-trivial, right? So if you take even a peak of an affine curve, and you even fix degree 0, this is in general very non-trivial. So this means we cannot use our intuition from differential geometry, but what we can do is check that indeed, if we could do what he said, that vect n x, let's say you can cover it with two open affines, and you call W the intersection, and you assume that in some derived sense and you write what the cotangent complex should be. You see, I told you that here it's infinitesimally trivial, but this is not quite true, because there is one bit which is not trivial, which is the H0 of the endomorphisms, which is not only not trivial, but extremely big. And so what happens when you go and compute the cotangent complex using this mysterious fiber product and pretending that all is well, you get exactly not just a cotangent complex, but you dualized, and you get exactly the Che resolution. So you get global section over U of at the point E on X, and this is, remember, this is in degree 1 less, minus 1, and you get this one, and then this goes to of W and E. And now all the weirdness, now that we are at the projective level, all the weirdness that there was, there were moduli, but there was no H1, completely disappears, because here the cohomology of this here is exactly what it should be. Here I get as cohomology the H0 of end E, and here I get the H1 of end E. So basically, what to a classical algebraic geometer is derived algebraic geometry has been developed in the last 20 years is to take this very naive intuition that to define a bundle over a union of two opens, you have to define a bundle on each, and then insist that they agree in the middle, and make it into a powerhouse that produces for you what you know you want. It produces a structure in which this is the actual cotangent complex. Now, in this case, it's not so interesting because on a curve, everything is smooth. But of course, I can do this for any number. It's just that this is easier to write. And so this means, for instance, that if I go to something which is smooth of a higher dimension, I will always get a perfect complex of amplitude depending on the dimension of the ambient manifold. And so this is why, in some sense, as a classical deformation theorist, this is where we want to go. Sorry? Sorry, I wanted to send it up and send another one down. Just give me a second. And then I want to put this one down. I think should be okay now. Not. Is the one behind visible? Not quite. I will lift it a little bit more. Okay, I think this should be it. Okay, and now back to what? Again, let me try to make connections. It's turned out to be surprisingly easy with what Mauro was saying. So Mauro said, usually, let me talk about a classical now moduli space, not moduli stack, is something that goes from affine to sets. And in some sense, the idea is that the derived moduli space is obtained by extending this functor. So remember, Mauro starts with an arbitrary derived stack, which is a map from derived affines to these S spaces. For some reason, I don't like spaces, so I tend to think of these as simplicial sets. It's not quite the same, but there is a strong relation. And so in one sense, what you want is that you have something from here, and this you get an induced thing here, and then this also is an inclusion, and you ask yourself whether this can be found. And this was the approach of Mauro. And my approach is mirror symmetrical. So I start with this picture. I have my classical moduli space. I have F, which embeds in differential F. And I have sets, which embeds in simplicial sets. And what I want is find a natural extension. So what I would like to think is that in some sense we should not really be defining the derived moduli space. We should just take the definition of moduli space as was said and extend it naturally. And if you recall, there was also a discussion that this part corresponds to the derived structure and this part corresponded. It's not true. You always need the simplicial sets because these are, anyway an infinity category. But informally, this comes with a relation to a higher structure. in particular, let me put it better, if this is a moduli space, if you go to sets, and before deriving you get a stack if original you go to groupoid, and 2 stack if you go to 2 groupoids, and so on, where at every step the point here is that sets are just the elements here where all higher cohomology vanish, higher homotopy vanish, and so groupoids are the one where homotopy from 2 and higher vanishes, and so on. So let me try and start setting up. Remember, we already know how to define this differential affine. These are these CDGAs in degree 0. And these are a priori just a category with homomorphism, which are homomorphism of complexes which are graded and respect multiplication. And then the approach in Mauro's lecture was that it was the throwing in the simplices and the it was the way we did the localization at quasi-isomorphisms that, by the way, this is something I should have said, that this is not unique, but it is unique up to isomorphism. Any two are isomorphic once I invert quasi-isomorphism, more or less by definition. But what I want to say is that I can already give some version of infinity category structure on this. And it's maybe not exactly the same, but I'm pretty sure it's a special case, because you still have to localize at quasi-isomorphism. But it has the advantage that it's a bit more geometrical, which is something I like. So let me make a detour, and let me, what time did I start exactly? 12 minutes. Okay. So what did I start with? Remember that if you want to work with topological spaces, the way you make them into infinity category is that inside topological spaces, you have simplices, right? And so what you want is that if you want an n map from x to y, this is just a map from x times the n simplex to y. And this has a lot of the structure I want. And by n simplex in topological spaces, I mean the set of x0, xn in Rn plus 1, such that for every I, xi is larger than 0, and the sum is 1. And these have all the natural maps you expect. So can we do this for CDGAs? Can we remember that now actually what I want is something like what would be the df? Remember, we are working on algebra, so everything works the other way around. So we would like to have an algebra of which that is the geometric counterpart. And what we can do is we can take C of x0, xn, and insist that, and we can view it as a free CDGA, but not in degree, not in degree at most 0. So this is not connective. So it's, if you want, this is the differential forms the algebra of differential forms. Remember, we had our original example, which were infinity differential forms on a manifold. And this is the differential forms on AN. But our AN, I view it inside AN plus 1, given by this. And so this is an algebra where in degree 0 you have this, and then in degree 1, so if you want, this in degree 1 there is the differentials, and in degree 2 then there is the double differential, and it goes until the n plus 1. And notice that the cohomology of this object now is what it should be. It's a C if I is equal to 0, and 0 for I bigger than 0. So this corresponds to our intuition that the simplex topologically is just a point. It's contractible. And this is also what this says, that this is contractible. And so now what is an N-map from A to B differential graded algebras? This is a usual map, a usual morphism from A to B. Let me call this Sn, tensor over C Sn. Yes.
How is that differential form and not just polynomial functions on the simplex?
Say it again.
I mean, how is the differential form and not just polynomial functions on the simplex?
Because I'm not insisting that the degree is 0. So if you want, it's free with also free dx0. Yes. Yes. So I'm just putting them in because now, sorry, no, you are right. I should have written like that. I'm adding those, and of course I'm adding that the sum of the differential should also be 0. Sorry, this I didn't write right. So let me just.
I guess sum of x should be 1 or something.
Yes, it should be 1. Yes. As you know, I'm just copying, but okay, minus 1 exactly. And this is the usual. Let me just rewrite this part so that it's more readable. Because this is actually important. So let me write Sn is C of x0, xn, dx0, dxn. These are in degree 0. These are in degree 1, so they anti-commute. And the relation, of course, the differential is given by d of xi is dxi, and d of dxi is 0. And then I have this, and I have this. And this has all the maps that simplices have, only in the other direction, of course. And so now you have an n map from A to B. It's just a map from A to B tensor Sn. And so you remember when I was vaguely confused earlier by Mauro, I said, how do I change degree? But the point is that if, for instance, my B is K plus, C plus C epsilon with a degree of epsilon is equal to -1, and I take S1, I take a B tensor S1, then now I have objects in degree 0 here. You see, if I take the degree 0 part of this, there is only the identity, because the epsilon is in degree -1. And remember, I also want the epsilon is equal to 0. But now I have that anything, now my epsilon times dxi is in degree 0. And so I can go there from, even if A is all free in degree 0, I can hit it. So this is, as I said, it's not, in some sense, it's much more confused and informal than what Mauro does. But on the other hand, I find it helpful because it gives me a geometric intuition of what is going on. And so in particular, when you do derived deformation theory, the first step, however, derived deformation theory, but still classical, so to speak, this sounds like a contradiction, is that you do differential graded art, but you still map to sets. You just look at isomorphism classes. And just as in the deformation theory in the stack case, just looking at the sets was enough to read off some information, this way, in the derived deformation theory, ultimately, we want that we have this, remember, sorry, here I forgot some op. So remember, what I have is that art is inside here, and I will define a differential graded, or this afternoon, a differential graded version of art, which is here. And so the corresponding map would go to simplicials, to S, to spaces. But of course, you can always go back from sets to spaces by taking pi 0. And so an intermediate step that people have studied widely is this part here. You take differential graded art, you put it in differential affine op, you map it to sets, but instead of defining that, which is complicated, you just define the pi 0. And this is what we will do this afternoon. Thank you.
Thank you. So we have some time for questions. Wait. You need to use the microphone because we are on video.
So the last sentence is to the simplicial sets. I mean, from as you define. I mean, from right from.
No, that is, well. As the point is, even from simplicial set, you can go to sets.
Yeah.
And what I'm saying is that there are theorems which only look in this, which use the simplicial set structure elsewhere, but ultimately compute, for instance, the higher tangent space in terms of this map. It's yeah, let's say this maybe will be more clear this afternoon, hopefully.
Should I think of these SNs as the standard simplicial and simplex in CD2As?
Yeah, you see, it's a very strange question because these are not differential affines, right? Because they are not connective, or they have terms in positive degrees. So in some sense, they don't exist in our geometry. But on the other hand, they really look like you know, a simplex. They have all the properties of n simplices. So long as I work in my differential graded algebras, the point is that these define a, how to call it, the notion of category enriched in simplicial sets on the whole category of differential graded algebras. And then I can take the full subcategory of connective differential graded algebras. I would be extremely happy if this could be made geometric, just because, as I said, I really find this intuition here very, very interesting. I find it that it helps me understand what's going on, and it would be nice to, but even if at the moment it doesn't, I think it's still nice to think of it as seeing that some derived structure is already in there without us having to localize to quasi-isomorphism.
Thank you.
Other questions? Let's thank Barbara again.